All right, I'll be talking first today. My name is Phil Swan. I represent the Atlantis Project, and I'll be talking about inertially supported launch infrastructure. So there's no question there's been a lot of excitement lately with TV shows like The Expanse and For All Mankind about the prospect of human civilization expanding out into the solar system. Lots of new companies have responded to NASA's efforts to commercialize space, and we've seen new countries invest in space exploration and achieve some impressive milestones already. We've also been making what I would call steady progress towards ever more remote settlements here on Earth and in near space. For example, we've established several modern bases in Antarctica and even seen a few bases in low Earth orbit. But we don't have any outposts on the Moon or on Mars yet. So why is that? I guess the first question we need to ask is whether the reason could simply be that these destinations are just too far away. So if you're a fan of space, and I'm sure you all are, you've probably heard of the halfway to anywhere aphorism. I think Robert Heinlein is credited with this idea, but it kind of goes like this. Jerry Pournelle says, "I see your problem. If you can get a ship to orbit, you're halfway to the moon." And Robert Heinlein replies, "If you can get your ship to orbit, you're halfway to anywhere." But at the end it says here, he was very nearly right. So let's take a closer look. Is it true that if you can get to orbit, you're halfway to anywhere? Well, distances in the solar system are vast, but distance is not always the best or the only metric that we should be considering when the journey involves orbital mechanics. Delta V is a more commonly used metric for this kind of travel, as evidenced by the large number of delta V maps you can find online. But delta V maps are a bit like subway maps. They explain how the stations are interconnected, but they aren't really a very accurate visual representation of the distances involved, or the delta V's in this case. Now, you can use these delta V maps to create kind of a stacked bar chart that looks like this. And if you put it in this way, it's easier to see from a delta V perspective that if you can get halfway to orbit, which is this blue line here, you are halfway to the moon. In fact, you're more than halfway to the moon, which is this bar over here. But you're certainly not halfway to anywhere. Like a lot of these other destinations are a lot further away from a delta V perspective. But that's okay. Like, for the gas giants, you probably wouldn't want to go down to the surface anyway. So perhaps Robert was thinking about places you might want to go, such as low Earth orbit around a planet or to a moon of a planet. So from this chart, we can see that you would be only halfway to low orbit around the moon, Mars, or Venus. So this is a chart for just low orbit around different planets. And still, these other planets are further away than halfway. But it's generally quite costly to accelerate and not so costly to decelerate, especially if you can use aerobraking for deceleration. If the planet has a suitable atmosphere, that's an option. So this is what it looks like if you add in aerobraking. So now you can't aerobrake on Mercury because there's no atmosphere, but other planets, there's aerobraking options. And so you can see now we're getting closer to this halfway to anywhere idea. This is the energy or delta V required to get to low Earth orbit, and this is the energy or delta V required to get to these other destinations. So we put a finer point on it. If we can get a ship to orbit, then from a delta V perspective, we're more than halfway to a handful of useful places. Part 2, Revenge of the Realities. First off, aerobraking is really quite challenging. For example, the shock radiation heating is proportional to velocity to the 8th power. Around 15% of the space shuttle's mass was for its thermal protection systems, just to give you an idea of how much thermal mass you need to absorb all the heat of re-entry. But if we want to have an outpost on the moon or on Mars, then we need to think about supply lines. And we'll need to rotate crews since we can't count on them to be willing to simply man these outposts until they die. So we need to consider the cost of operating supply lines and how that's affected by the return trip, that is, the people, the provisions, or samples you might be bringing back from these other destinations. There's also the desire to have shorter duration, higher delta V trajectories to minimize exposure to space radiation. And finally, there's the tyranny of the rocket equation. Recall that the one-way trip to Leo was more than halfway to a few useful places from a delta V perspective, but if we consider the round-trip delta V, it looks more like this. The return trip, even with aerobraking, increases the delta V requirements significantly. In fact, if your discussion is about round-trip missions, the halfway to anywhere aphorism really only applies to the delta V to the moon, and almost to Mars. Now, we haven't talked about other factors like mass budget for provisions or the desire to use these higher delta V trajectories to reduce the crew's exposure to space radiation, but these are more complex topics. What I really want to do next is call your attention to something far more significant. You see, the purpose of an aphorism is to express a general truth or principle about space travel in this case, in a concise and clever way. But the truth is that go, no-go decisions about space missions are not based on delta V. They're based ultimately on cost. Delta V is not the same as cost. In fact, because of the rocket equation, the relationship between cost and delta V for most mission architectures is actually exponential. So in this chart, I've plotted delta V, cost versus delta V, and I added vertical lines to show the delta V to various destinations like LEO, ISS, the orbit, Earth escape, moon surface, etc. I also added two curves, this green curve and this blue curve, to represent Falcon 9 just putting a satellite in orbit and Falcon 9 doing a resupply mission to the ISS. Now, if you want to use Falcon 9 just to go to LEO, then the cost per launch after correcting for inflation is about $72 million today. You get to divide that number by all the mass that you can put on top of the rocket and inside the fairing. Now, the fairings are jettisoned early in the mission, so most of the mass makes it to orbit. But in this case, there's no return option for that cargo, other than perhaps waiting for its orbit to decay and having it eventually re-enter the atmosphere. If you want a return option, which is something you need for important classes of missions, such as resupplying the ISS, then you're going to need to add abort systems, for example, to reduce the risk to the crew, and lots of other components like heat shields and things like that. So first, the cost per launch goes up from 72 million to around, I think it's 287 million per launch. That's what NASA and the taxpayers pay for those launches. And second, the amount of payload you can deliver to the target destination drops from around 10,000 kilograms to around 3,307 kilograms for resupplying the ISS. And this is because a lot of the space or mass of the cargo on top of the rocket is allocated to those abort systems, the life support, the heat shield, these kinds of things. So the net effect of all this is that the cost per kilogram for resupplying the ISS is around 10 times higher than the cost just to go to orbit. In fact, we've heard a lot about how launch costs have been coming down over the years. A lot of this is really just sort of refocusing our efforts on or our thinking on the low Earth orbit cost, not the cost of resupplying the ISS. If you look at the cost of resupplying the ISS, it actually remains stable over the years. In fact, it's going up slightly, not coming down. But the takeaway here is that it costs in the range of $6,000 to $20,000 per kilogram to send a payload on a one-way trip to low Earth orbit. It costs about $80,000 a kilogram to resupply the ISS. It costs around $1 million per kilogram to go to the surface of the moon or to Mars. Actually, 1.2 million is more accurate now. And I don't know what it costs to do a round trip to the moon or Mars, but recently there were independent reviews of the Mars sample return mission, which placed the cost at about $8 to $11 billion. And so if that's an indication, it's going to be quite expensive. So I plotted some of these empirical data points on this graph here to help illustrate that there is an exponential relationship between cost and delta V. So this is a log graph on the side, and this is kind of where the line fits through these 4 data points I just mentioned. So the bottom line is, from a cost perspective, if we can get our ship to orbit, we're not really halfway to anywhere at all. If we find a point on it, we're only a small percentage of the way there. So about 0.64% of the way there to the moon, and if it's a round trip, we're at 0.0000786% of the way there from a cost perspective, if we're in orbit. Unless, and I'm pretty sure some of the smart people out here in the audience are already thinking of some unlesses, like what if we refuel on the moon or on Mars, right? I call these things infrastructure. Refueling on Mars requires infrastructure. So part 3 is about A New Hope infrastructure. So most of us are space nerds, right? So we think that giant rockets are really cool. It's in our DNA, that's never going to change. Yet we can spend hours driving down the highway and we don't stare out the window at the immense scale of the interstate highway system in awe. But it's almost 47,000 miles long. We accept that power is freely available. We do not really appreciate that the US electrical grid is the largest interconnected machine on Earth. It is 160,000 miles of high voltage power lines. And we take it for granted now that data from anywhere in the world can be retrieved and instantaneously transmitted to us, and yet we are not awestruck at the scale of the network of undersea cables that makes this possible. Cables that did not even exist before 1988. The space shuttle was launched in 1981. As of 2024, there are 1.4 million kilometers of undersea cables. And as you can see from this cross-section up here, they're not trivial, they're not like a thin little cable. These are complicated cables. This is infrastructure. Infrastructure can be game-changing. But how can we use earthly infrastructure to solve a space problem? Well, we already established that rockets scale exponentially. But the cost per kilogram for a mass driver does not scale exponentially. Now, the structure for mass driver designs, like the basic physical structure, such as coil guns and rail guns, this scales with a square of the exit velocity of this launcher, because v squared equals 2ax, high school physics. But if the mass driver uses pulsed power electronics, and most of the designs people are familiar with do, then that cost generally scales roughly with the cube of the exit velocity. And it's this cube effect that makes these traditional mass driver designs expensive for space launch, especially when most of the demand is for access to low Earth orbit, where rockets already do a pretty good job of serving that market. Still, v cube scaling is significantly better than exponential scaling. But as demand starts to shift from LEO to destinations such as the Moon and Mars, the exponential relationship between delta V and cost starts to take a heavy toll on rockets. Now, this curve here, is this red curve I've added to show you what a mass driver might look like. Now, this is a tool that actually you can play with lots of parameters and see the curve change with different mass driver designs, but it gives you an idea that this whole market up here is starting to be opened up by the fact that we've changed the scaling relationship between cost and delta V significantly. Just going from exponential to squared or cubed is a huge improvement in terms of what the best solution becomes. But down here, where we're doing low Earth orbit, the cost isn't that significant. The cost curves for these different launch systems is actually quite a complex topic, but if you're interested in learning more on this, I've created this tool that you can find on GitHub, and it will be released on the Project Atlantis website soon, which will enable you to interact with it, and you can change some of the parameters like I'm showing up here and see what the curves do. So over time, we'll add more and different types of launch systems to this tool and make it easier for people to compare them. But for now, I'd like to discuss how we can make launch technology that scales with velocity squared instead of velocity cubed. So last year, I presented on a technology called the variable pitch screw launcher. You can find that presentation on YouTube if you're interested. But what you need to know is, for this presentation, is that the twin screw launcher is designed in such a way that it doesn't require pulse power electronics to operate. And as a result, the cost doesn't scale with a cube of velocity. It scales instead with a square of velocity. So it performs significantly better from an economic feasibility perspective. This is a 3D capture from our digital twin. In this case, it's running a simulation in real time, and it's currently configured so that the vehicle takes about 2.5 minutes to get into space, so that's how much time I've given myself to explain this technology to you. The basic high-level idea is not particularly new. We build a mass driver, which is kind of like a linear motor, on the ground, and we use that to accelerate a sled. And the sled accelerates along this track. We place our vehicle on the sled, and the track, the sled, and the vehicle all travel within a tube, and we pump the air out of the tube to minimize air friction during the launch. So instead of using Lorentz forces like a railgun or switching magnets on and off really fast, like a coil gun or a quench gun, the variable pitch screw launcher uses spinning screws. The sled is designed to couple to the screws flights magnetically, but the magnets don't need to rapidly switch on and off. It's more like the sled is pulled along by a mechanical wave, so no switching is needed. This is how the architecture achieves velocity squared scaling instead of velocity cubed scaling. Also, there's no direct contact between the sled and either the screws or the rail. The sled is magnetically levitated above the rail, and the grapplers hover over the screw flights and sort of pull on it magnetically. So when the sled reaches the end of the acceleration section, which we aren't quite at yet, but we're going to get to it soon, it'll travel up a ramp which needs to be constructed on the side of a mountain. So this diverts it towards space. And when the sled reaches the end of the ramp, the spacecraft separates from the sled and continues on a ballistic trajectory through an extension of the evacuated tube and then into the upper atmosphere. The sled stays on the track and it needs to decelerate hard so it can circle back to be reused again. So the vehicle exits this evacuated tube, this extended evacuated tube, and lights its rocket engine at the end and travels to the atmosphere. Now the vehicle is very streamlined to minimize aerodynamic drag and, more importantly, aerodynamic heating. So here we have it now in the upper atmosphere. So once the spacecraft reaches apogee, it'll fire its engines once again to circularize its orbit, or if it's headed to the Moon and Mars, it'll depart Earth on a hyperbolic trajectory. And I just stopped the camera moving so you can see it disappear into the distance. So we're making excellent progress on modeling this. In fact, I have a prop to show you. I brought along a 3D printed screw flight for you to see for a small scale prototype we're developing. But what I wanted to talk to you about today was the problem of the suspended evacuated tube that we saw at the end of that last video. Now, the suspended tube has an airlock at the end with fast doors so that the spacecraft can exit without the air coming back in. And that could also be used you could use some sort of plasma window technology for that. We need this tube to prevent the sonic boom near the ground, so it'll be quieter if it travels through a tube up to the upper atmosphere. It also, having the evacuated tube extend up into the atmosphere more, reduces the stress on the vehicle's thermal protection system. So there's a trade-off there between the cost of the tube and the cost of the thermal protection system on the vehicle itself. And it also helps preserve some of the delta V that the variable pitch screw launcher imparted on the vehicle in the first place. For supporting the tube, we've been kicking around a number of options for this. Option one is to build in very high altitude land, like for example the Tibetan Plateau. Now we could do that, like India could do that, or China could do that. If India did it, they'd probably have to launch over China, so I'm not sure how that would work out from a geopolitical perspective. But certainly China could build on that plateau, and they'd be already up at 6 or 7 kilometers above sea level for that. Option number two is to support the tube with balloons or drones. Ingenuity demonstrated that drones can fly at very high altitudes, or in the case they fly on Mars where the atmosphere is very thin. But winds or maintenance might be more of a problem for this. So I feel like drones or balloons might be more of a short-term solution. I think perhaps the best long-term solution is something called inertially supported structure. This would be a cable traveling inside an evacuated tube on magnets. And the complexity is similar to that of the undersea cable that I sort of showed you earlier, right? So you'd have a kind of a moving part on the inside and traveling on magnets through an evacuated tube, which it would look different than this, but not much more complicated than this. Well, this is a fiber optic cable, though. So this is something that's also been presented in the past. Lots of people have presented things like space cables and Lostrom loops. Here's an image of something presented by John Knappen, not too far back, like in 2013, I think. But what I'm proposing is something of a more scaled-down version. These ideas are literally used to launch the vehicle, and I'm proposing that we can do this just to support the evacuated tube. So it would be a scaled-down version of these ideas. And the tube is very lightweight. It's filled with a vacuum, and it's just basically got to be held up. Now, we do have some real-life experience with the concept of a mass stream. So this is an oil well that had an accident. I'm saying that this drill that's coming out of the well is a bit like a mass stream that we'd have inside a mass driver, except it would be magnetically confined and controlled in an actual mass driver. But it gives you a sense of, like, this is just a piece of metal coming out of a hole in the ground, and it's able to actually support itself high up in the air. All right, recapping. So there is a need to shift our focus from low Earth orbit to the Moon and Mars. I think we all agree with that. The aphorism, you can get a ship, if you can get a ship into orbit, you're halfway to anywhere. It's really about delta V, and it's only semi-accurate. There is an exponential relationship between cost and delta V when the transportation systems are governed by the rocket equation. And there's a V cubed relationship between cost and delta V when the mass over cost is dominated by pulsed power electronics. The variable pitch screw launcher, though, has a V squared relationship with cost, and this is game changing. So in light of where we want to go, which is the moon and Mars, we must employ mission architectures where the technologies scale with V squared, not the exponent of V. And inertially supported active structures are a key enabling technology in the long term. Now, we can support an evacuated tube with drones in the short term, but long term, we need something like this inertially supported active structure. So final thoughts. Someone recently asked me, why choose Hawaii for that visualization I just showed you? Why Mauna Kea? Why choose that mountain? I thought about that, and there are lots of mountains that could be used to support the ramp, especially if they can figure out a good way to support the evacuated tube. At least for traffic to Mars, the launch windows only occur every 2 years or so, and so we'd really just be using this infrastructure every evening for a few hours for the launch window time of a few weeks. So it's something that would happen occasionally, not all the time. So it's not like there needs to be continuous launch activity. But I think I chose Mauna Kea as a nod to the adventurous Polynesians who ventured out in the Pacific Ocean many years ago with only the stars to guide them. And these people really inspired me, so I decided to show what the launcher might look like if its upward curving ramp were supported by Mauna Kea. I guess I thought it would be fitting if after the stars guided us to this mountain, the mountain guided us to the stars. So any questions? Yes?
Any question between the distinction between cost and price? You were using the word cost. Do you really know the cost, or were you talking about price?
Well, we know the cost to consumers and the taxpayers and NASA because we have data from reputable sources. So I got my data from several sources. In fact, I published on this at Ascend last year. But there's the Office of the Inspector General reported some data. NASA had a press release. I used that. There's USAspending.gov I used. And
about the cost to SpaceX, because obviously if the government's willing to pay and there's no competition, you wouldn't have any real incentive to lower your prices. So the question here is what could they lower the price to if there was competition out there?
yeah, that is a good question. Yeah, so there has been competition for a long time. And if you actually look at what people are actually spending on the rockets versus what might be posted as a price on the website, there's a significant difference there. And I wrote a paper on explaining some of the reasons why the difference exists. It's a little bit of hype. Like when people make early statements around the costs, there's hype. But later on, when the projects are actually operational, there's more subtle reasons why the costs and the prices are different. Like I said, for example, conflating the idea of going to the ISS and returning with the idea of just putting a satellite in orbit, there's very different prices or costs for those two different missions.